In this video, we're going to look at improving on the magic number, and in fact we're going to generate 10 different magic numbers. Now don't worry too much about the mathematics. What matters is that you are able to follow the general principles of what I'm doing here. Now we've seen in the previous videos that we can generate the magic number from the simple equation 3 divided by 2 L times B. And you can see that in this equation here. Now, from the previous videos, we've seen that we generated an approximation to the logarithmic function log to the base 2, 1 plus mx. And we approximated this with a simple linear approximation mx. Now we're going to add in an extra factor in this approximation, and the extra factor is called alpha, and alpha is a little parameter that we can change in order to adjust this approximation. So let's have a look at this in the graphical calculator. So we start off with the function we want to approximate, which is log to the base 2 1 plus x. Now, as I noted in the previous videos, the value of x is our value m, but I have to use x within this tool in order for it to print the graph off. Now we can approximate this using the Taylor series approximation, and we've seen that in the previous video. So that's the Taylor series approximation, and you can see it's a really cool approximation until around about 0.8, in which it starts to tail off. But we didn't want to use that because it's too complicated. So we used the approximation, which is y is equal to x, which is a simple linear approximation. Now we're going to adjust this so that we add in the extra parameter. So the extra parameter is nothing other than just the crossover point of this line. So for example, if we have this parameter here, y is equal to x plus alpha a. Now here's the value here for alpha a, so we can adjust the approximation to this line. Okay, so in effect all we're doing is we're adjusting the y-intercept. So we're just instead of doing the approximation y is equal to mx for a simple line, we're doing y is equal to mx plus c. Okay, so that's all the value of alpha does. It adds in this extra term, and you can see here that if we wanted to approximate this between 0 and 1, we could have it somewhere sitting down around about 0.05. Okay, so at that point the approximation here is off at the bottom and it's off at the top, but it gets closer the rest of the way through the actual curve between 0 and 1. Now the question that we have is, how do we actually choose this value for alpha? So we want to minimize the difference between the blue curve and the pink line. So it's a question of minimization, and there's different ways of minimizing these differences. So the one that we're going to look at is a typical one that's used within engineering, which is called the root mean squared. So let's go back to our equations and we'll see this root mean squared. So when we add in this extra term alpha, it has the effect overall of changing the value of b to the value b minus alpha. So that's all we really need to know from the little bit of mathematics here, is that the value for b now becomes b minus alpha. So whenever we want to generate the magic number, it's going to be generated by 3 upon 2 L times b minus alpha. Now, as we mentioned, we want to choose a value for alpha, and alpha is just really the y intercept of that line y is equal to mx. Now we're going to do it using the root mean squared. So this is a common method within engineering. What we do is we take the value of our function y and we subtract off the other value for the other function x, we square it, and in this instance here I've actually worked through a piece of code in Python which does this for 1,000 values between 0 and 1, and we add up all of these values, and again we divide it by 1,000 and take the square root. Now I'm not going to go over the reason why this works in this video, and it's out with the scope of the video, but I may well produce another video on the RMS values and fairly soon, so this will be available within the YouTube channel. So we're going to do this with the value yi, which is log to the base 2 1 plus x, and the xi is the x plus alpha. So remember, this here is nothing other than just an equation of a line y is equal to mx plus c. So I've already gone ahead and generated that code within Python, and I've worked out from that code the value of alpha, which minimizes this RMS value for those 1,000 inputs from 0 to 1. And the value for alpha I get whenever I run that code is 0.05725. So let's go and we'll put this into the graphical calculator and we'll see how this changes the line y is equal to x. So we started off with the line y is equal to x, but now we're going to replace this with the line y is equal to x plus alpha. In this instance, we noted that alpha is 0.05725, and I generated this value of alpha using the RMS values. So I've minimized the root mean squared values over 1,000 points from 0 to 1, and it's given us this value here. So you can see that's the line here in pink. So I'll get rid of the y is equal to x. So this is our new approximation. So let's have a look and we'll see the actual values for this approximation. So if we use this number here for alpha, then the magic number we're going to get is 3 upon 2 times 2 to the 23 times 127 minus the value of alpha, which is 0.05725, and this gives us this number here, and this is the number in hex. And whenever we compare this number to the actual magic number that is used, then it's within 99.99% of that magic number. Now you may well ask, why is it that we cannot get the exact magic number? Well, the exact magic number was generated by taking the next step in our algorithm, which is the Newton-Raphson. And we're going to do the Newton-Raphson first for 1 and then 2 iterations. Now, whenever they generated the actual magic number, they took the mathematics of the Newton-Raphson and they employed that mathematics within what we have seen over the last few videos. And they generated the magic number taking that part of the mathematics into account. And that's why the magic number is different from what we see here. But we're not going to go through all of the details of the mathematics of how they did that. It's out with the scope of what we are doing here. We're really just wanting to have a good indication of where this algorithm has come from. And I think we've got enough detail so far. I may well go through in another video at some point and see if I can get to the exact magic number. But we're not going to be able to do that here and now and we don't really need to do it. We've got a good enough approximation. Now there's one other thing that we want to do before we finish up here, and that is I have another method which we're going to try out, and that is we're going to generate 10 different magic numbers. So let's see how this is going to work. Now I wrote another piece of Python code which generated 10 different magic numbers. So what I did was I worked out what the optimal in terms of the RMS value was for the magic number between the inputs of 0 and 0.1, and then the inputs 0.1 to 0.2, and so on and so forth, all the way up to 0.9 to 1. So I've generated 10 different magic numbers that we can use depending on the inputs. So let's see this in the graphical calculator. So what I have done here is add the 10 magic numbers which we have generated and drawn each of the approximation lines. And you can see these lines here. So if we were to pick just one set of values, say from 0.2 to 0.3, then you can see here that we're going to use the magic number which will give us these approximations. So this will be the linear approximation from 0.2 to 0.3 of the function log to the base 2 1 plus x. And you can see here that there will be a discontinuity here. So whenever we have a point here at 0.2 and then the next point along, there will be this jump. So it'll be interesting to see exactly the issues that may occur due to this jump. But we'll see that whenever we actually build the circuit in Logisim. So this was the route that I was intending to take in order to give us a more accurate first guess at the reciprocal of the square root. So I decided to work along this route here because it's something that's kind of new for us and kind of bespoke, and something that we can do in order to generate something that is relatively new and unique for our own purposes, and it'll be a nice learning experience as well. So that's all for this video. In the next video we're going to have to look at the Newton-Raphson method, but we've already covered this in the previous videos on the courses on designing the CPU. So thank you for listening. I'll get you on the next video. Goodbye.